Okay. So this is a new talk about an old subject for me, which is minimal asymptotic bases. So we can start with some general class of questions. Suppose you have an infinite set of equations with the property that every equation in the set has at least one solution. Or maybe not every equation, but all but finitely many of the equations have a solution. Or even there's some infinite subset of the set of equations and every one has at least one solution. Does some equation then have at least two solutions or three solutions or arbitrarily many solutions or infinitely many solutions? Right? So does one imply two or more? Well, maybe it doesn't. So if the answer is no, we can modify the question. We can say, well, suppose you have an infinite set of equations with the property that every equation has at least two different solutions. Or finally, many equations have at least two solutions, or maybe an infinite subset of the set of equations has at least two solutions. Can you then say that every equation or some equation has at least three solutions or four solutions, or arbitrarily many or infinitely many? And so on. So here are two examples or some examples of problems of this kind. So the first is infinitely old. We take a set of non-negative integers and we say it's an asymptotic additive basis of order h if every large integer is the sum of h elements in the set. And for every positive integer h, the additive representation function, r of n, it counts the number of ordered representations of n as a sum of h elements of a. So this says that this equation, a1 plus a2 up to ah equal n, has at least one solution for all but finitely many n. So this equation has at least one solution, and Erdős and Turan asked approximately 70, 80 years ago now, whether the representation function must be unbounded. So if every equation has at least one solution, can you find for any number k an integer n with at least k solutions? Is this representation function unbounded? And an equivalent way to write that is that they stated the problem for two sum n's, but if the lim n for the representation function is at least one, does that imply the lim sup is infinite? So Erdős and Turan stated this for sums of two elements, and in general, the slightly more general question or conjecture is whether it's true for h sum n's, but this is completely unsolved. This is an ancient problem that has been around for a long time. Now there's a multiplicative version of this. We can say that a set of positive integers is a multiplicative basis or an asymptotic multiplicative basis. That means every sufficiently large integer is the product of h elements in the set. And we can count the number of representations of an integer as a product of h elements in the set. That's this function g of n. B is the set of positive integers, h is the number of factors. And we say that the set B is an asymptotic multiplicative basis of order h if every number from some point on has at least one representation as a product of h elements in the set. So this is the beautiful, simple multiplicative analog of the additive question. And Erdős proved the multiplicative analog of his conjecture. So in 1964, this was a paper in the Israel Journal of Mathematics, Erdős proved that if you have an asymptotic basis of order 2, then the multiplicative representation function is unbounded. So that means that if you have a set of positive integers with the property that from some point on, every number is a product of at least two of the integers in one way or another, then they're integers with arbitrarily large numbers of representations. And Erdős's proof was graph theoretic. It used graph theory. And maybe 20 years later, two Czech mathematicians, Nathanson and Gödel, were able to give a simpler proof using Ramsey's theorem. They took the basic Ramsey theorem, which is not a trivial generalization, but a generalization of just the pigeonhole principle. Pigeonhole principle for infinite sets is if you take an infinite set and you write it as a union of a finite number of subsets, one of the subsets has to be infinite. So that's the first case of Ramsey's theorem. And the more general case is kind of a multiple induction on that. And using a kind of iterated form of Ramsey's theorem, Nathanson and Gödel gave a very beautiful proof of Erdős's theorem. And you can modify the Nathanson-Gödel proof a little bit and get the same statement for asymptotic bases, multiplicative bases of any order h greater than or equal to 2. Now, there is a natural generalization of a multiplicative basis, and it's the following. Suppose instead of taking one set of positive integers, you take h sets of positive integers. They do not have to be disjoint, pairwise disjoint, or they don't have to be disjoint in any way. You simply have h non-empty sets of positive integers, and you consider how many ways you can write an integer n as a product of h factors with one factor coming from each of these sets. And this is the multiplicative representation function for this multiplicative system. So if all the sets are the same, it's the Erdős case, but this is a tad more general. And we say that this h tuple of sets is an asymptotic multiplicative system of order h if every number from some point on has a representation like this. So here's a very simple example of a multiplicative system. Take the prime numbers, partition them into h pairwise disjoint non-empty sets. And for each I from 1 to h, let bi be the set of positive integers, all of whose prime factors come from the set capital P sub I. So an equivalent statement of the fundamental theorem of arithmetic is that every integer can be written as a product of h numbers, one from each of these sets, and in a unique way. Notice if you take, like 1 is in each of these sets, because every prime factor of 1 is in P1 and P2 and so forth. So the fundamental theorem of arithmetic says that for this multiplicative system, the representation function is equal to 1 for all 1. And so the lim_inf is 1 and the lim_sup is not infinity. The lim_sup is also 1. So the analog of Erdős's theorem on asymptotic multiplicative bases is false for these multiplicative systems. But that the example is misleading, right? And I know because I talked to Erdős about this. Erdős was misled by this example. He looked at this and he stopped. So let's look at this a little bit more carefully. Suppose this is some multiplicative system, B1 up to B8. So these are h sets of positive integers. No conditions on them, they're just h sets of positive integers. They don't have to be disjoint or pairwise disjoint, but it does have the property that from some point on, every positive integer can be written in at least one way as a product of an integer in B1 times an integer in B2 and so forth up to an integer in B sub h. And for this set, so, and let M of h, so fix h is the number of factors, the number of sets in this h tuple. For any multiplicative system, which an asymptotic multiplicative system, that S be the lim-inf of the representation function. So if it's a multiplicative system, this number is at least 1 for all n from some point on. So the lim-inf is some positive integer S, and let T be the lim sup. So a long time ago, I proved the following theorem. What is this set M of h? So you can have S equal to 1 and T any integer, any positive integer, or you can have S equal to 1 and T equal to infinity, or you can have S being any number from 1 to h and T equals infinity. But that's a complete description of the set M of h. And it follows from this that if the lim-inf of this representation function, so this says if every integer from some point on has at least 2 representations, then the representation function is unbounded. So this is a pretty example of that sort of general problem I stated at the beginning. So in this case, we have a setting where you have a set of equations. The equation is write n as a product of h integers, one factor from each of the sets. If every equation from some point on has at least 2 solutions, then you have arbitrarily many solutions. There's some, for any number n, for any number k, there's a number n with at least k ways, at least k representations as a product of h factors from the set. I like this theorem for 2 reasons. The proof uses Ramsey's theorem. It uses the Nestor-Riddle idea of applying Ramsey's theorem to this problem multiplicative number theory. It also enables me to make the following statement. There is a well-known journal. Oh, and this paper was published in the Israel Journal of Mathematics, which is a well-known journal. There is a less well-known journal called the Palestinian Journal of Mathematics. And as far as I am aware, I am the only mathematician who has published in both journals. So, curious. Okay.
Any further remarks?
Excuse me?
Nothing. No,
it's like, you know, it's a journal. They're journals, but I've just noticed, because I look at both journals, that the sets of authors tend to be disjoint. So that's all. But it's not completely disjoint, because there's at least one element in the intersection of the sets of authors of the 2 journals. All right, let me get back to the additive problem. So we have sets of non-negative integers. If A1 up to AH are sets, the usual definition of the sum set is every integer that can be written as a sum of H summands, one from each of these sets. And in the case when all the sets are the same, we call it HA. And we say that a set A is an asymptotic basis of order H. If this HA, if this H-fold sum set contains all sufficiently large integers. And the Erdős-Turan conjecture says that if the lim-inf of the representation function for the additive problem is at least 1, then the lim sup is infinity. So if you want to, one way to study this is to look for additive bases that have, well, I mean, there are 2 possibilities. It's true or it's false. If it's true, it's true. If it's false, there's a counterexample. A counterexample would be an asymptotic basis, additive asymptotic basis, that has a bounded representation function. So a strategy to construct a counterexample is to look for additive bases that have a small that have small representation functions. And you can take small in a variety of ways. And one way of several is to look for an additive basis which is minimal in the sense that no proper subset is an asymptotic additive basis. So if that's the case, that means if you take any element from the additive basis A and remove it, it's no longer an asymptotic basis. So infinitely many numbers are no longer represented. So that means that there are infinitely many numbers which have exactly, well, I shouldn't, in the case of H equal 2, it would mean infinitely many numbers with exactly one representation. For order H, it means infinitely many numbers where every representation requires this fixed element. So this statement is incorrect. It should be for H equal 2, and there's the slight refinement for H bigger than 2. In any case, the construction and classification of minimal asymptotic bases is a problem of independent interest in additive number theory. So in a certain sense, it arose from the Erdős-Turan conjecture. It also arose independently of it. It's a natural object to consider. And, but it's not obvious that such extremal sets exist. So if you take a basis, all right, a basis means every number, not every sufficiently large number, can be written as a sum of H elements from the set, then it's easy to show that every basis must contain a minimal basis. Namely, you start to throw away things and there's a little inductive argument and you can construct a minimal basis inside every basis. But for an asymptotic basis, that's not true. And in fact, one can show that you can find additive bases of order H which do not contain a minimal basis. In fact, the nicest example is of the following sort. You can find an asymptotic basis of order H with the property that you can throw away any finite subset and still is a basis. But if you throw away any infinite set, it no longer is a basis. And since they teach you in preschool or somewhere that there is no maximal finite subset of an infinite set, it means that such a basis does not contain a minimal asymptotic basis. But minimal asymptotic bases do exist and they've been constructed. And the first examples were constructed in the following way. They use what is called the geodetic representation of an integer. So you fix an integer g at least 2, and every positive integer is uniquely, has a geodetic representation to some xij to the power I, where the digits, the x sub j's, are between 0 and j minus 1, and the xj's are 0 from some point on. So, binary, base 10, whatever is your favorite. And the first explicit constructions of minimal asymptotic bases use the two-adic representation of the positive integers. So a construction goes as follows. So let W be any non-empty set of non-negative integers, and let F star of W be the set of all non-empty finite subsets of W. And let A2 of W be the set of all numbers of this form. This xj shouldn't be there, xj is 1. This is just, you take a finite subset, you take a finite set F, and you look at the powers of 2 corresponding to the elements of F. So this x sub j is just 1. So this is, so if you have a set W, this is all the numbers you can write as sums of powers of 2 that are in the set W. And since W is a set of non-empty finite subsets, 0 is not in here, right? So the F is never the empty set, so there's always some power of 2. And there's the following theorem, which says that if you let W, so you fix an H and you let it Wi be all the integers I congruent, all the integers n congruent to I mod H. So A2 of W, so W0 is all the multiples of H. So A2 of W0 is all numbers that are sums of powers of 2, where the power is a multiple of H. And in this set, you have sums of powers of 2, where each power is congruent to 1 mod H and so forth. So this is a minimal asymptotic basis of order H. So in proving something like this, there's a very simple lemma, which is the following. I think of this as like an exercise in physics. You have particles and things build up from the particles. So you take W1 up to Ws, these are distinct non-negative integers. And X1 up to Xt, these are not necessarily distinct non-negative integers. And the sum of the powers 2 to the Wi, I going from 1 to S, so the sum of the 2 to the W's equals the sum of the 2 to the X's. And the little lemma says you can take the numbers from 1 to T, partition them into S different subsets, such that each of these powers 2 to the Wi is a sum over the elements in a particular subset. And yeah, so it's like physics kind of. And it's not true if you replace 2 by something bigger than 2. Okay. Now, there's a generalization of the geodetic representation of an integer. So it's script geodetic. So script G is a sequence of positive integers strictly increasing. G naught, the first term is 1, and each term divides the next term. So you can think of G sub I to be G to the power I, and that's the geodetic sequence. And you let D sub I be the successive quotients, because the sequence is strictly increasing. Each of these is at least 2, and GI is a product of these divisors, and these are very nice properties. And the arithmetical fact is that every integer has a unique script geodetic representation. So you take a positive integer n, you can write it as summation xi g sub I, where the x sub j is in this set, dj plus 1, these are the successive divisors, and the digits are 0 from some point on. So you're familiar with this when g sub j is just a fixed g to the power j, but that's what it is. And as we did with the two-adic numbers, suppose we take any set W of non-negative integers. We let F star of W be the set of all non-empty subsets of W. And we let A subscript G of W. This is all the numbers that you can write in the form X summation xj gj, where the gj's come from the set W, and the xj's are the digits in this appropriate interval. And again, because the empty set is not in here, 0 is not in any one of these sets. This is a set of strictly positive integers. So we take the non-negative integers, we partition it into H non-empty pairwise disjoint sets. And for each of those sets, we can construct the corresponding set A sub G of W. And we take the union of those A sub G of W's. It is not a basis of order H, but it is an asymptotic basis of order H. And in fact, when you take the H-fold sum of this set with itself, you get every number n greater than or equal to H. So it's natural to try to figure out whether a set of this form can be a minimal asymptotic basis. And sometimes it is, and sometimes it's not. So for some, but not all partitions of it should be the non-negative integers, this construction produces minimal asymptotic bases. So here is a simple example. Suppose we just take h equal 2, and we partition the integers into two sets with the property that each of the sets contains infinitely many pairs of consecutive integers. In that case, when you take AGW1 and AGW2, that is a minimal asymptotic basis of order 2. And we want to extend this a little bit. So I mentioned that lemma where you have sums of powers of two, distinct powers of 2 equal to sums of not necessarily distinct powers of 2, and you can partition the powers of 2 on the right to give you each power of 2 on the left. That's not true for arbitrary G. In order to prove a kind of base G result, Jing de Jia extended that theorem a little bit, and Jia's theorem can be, Jia's lemma can be generalized a little bit more, and you can get a statement like this. I mean, it's a technical statement, but it's really very subtle in its way. So you take this script Geodetic sequence. So these are positive integers, strictly increasing. Each term in the sequence divides the next. We take P pairwise distinct elements, so I can write them as a strictly increasing finite sequence. And I let Vj be a not necessarily a sequence of not necessarily distinct integers. And I have that this number n is summation xi g sub ui, but it also can be written like this, where the xi's are the digits are the appropriate digits. Now on the left, since the g's are distinct, this is the script Geodetic representation. This is not. And you might say, well, can you partition these things so one of these terms, some set of these terms gives you each of these terms? And the answer is no. You can actually construct some counterexamples. But Jia's idea, which is generalized here a little bit, says the following. If I take some initial segment of this series, so instead of summing from 1 to P, I sum from 1 to K. And because these numbers are strictly increasing, the largest of the UIs is U sub K. And on the right-hand side, I look at all the terms Yj, G, V sub J, where the Vj is at most the U sub K. So I have an inequality of this sort. And so, yeah, you have to kind of like arithmetic to do this. So here's an example of a sort of theorem you can prove. So fix an integer h, at least 2. We're going to be looking at h-fold sums. Let t be an integer at least log h over log 2 plus 1. Partition the non-negative integers into h pairwise disjoint sets. Then, and suppose, so what this sort of technical statement says, that when you partition this, when you partition the non-negative integers into these sets, every one of these sets contains an interval of t consecutive integers. And not only does each set contain an interval of t consecutive integers, each one of these sets contains infinitely many intervals of t consecutive integers. So that for each I, there's an infinite set script mi, and for every number mi in this set, this is the interval of consecutive integers starting at mi minus t plus 1 up to mi is contained in wi. And then you take any Geodetic sequence and you take the numbers that are constructed. So this set is just all the numbers whose Geodetic representation only uses the GIs in the set W sub I. And this always gives you a minimal asymptotic basis of order H. So this is exactly the opposite of the first example I showed of a minimal asymptotic basis. In that first example, I fixed a number h, and I partitioned the integers into h sets. Each set was all the ith set was all the numbers congruent to I mod h. So those sets were arithmetic progressions with common difference h. So you had no string of consecutive integers. You don't even have two consecutive integers. So that in some sense is like the opposite of this construction. And I'm not going to give the proof of any of this because it's very detailed and I don't like giving proofs in talks. And there's a version of this paper on arXiv, and there will be very soon, as within the next week or so by Thanksgiving, a much better version if anyone is curious about the details. So, but there are some open problems here, which is, and this is really kind of a mystery. Suppose you take the non-negative integers and you partition it into, this should be h minus 1. You partition it into h minus 1 subsets. And you take a geodetic sequence, and so this AG of W, this is the set of positive integers that come from this partition. And I'm going to throw in 0. Right? In the previous examples and in the theorem, I was looking at a set of strictly positive integers. There was no 0. 0 is sort of curious. And you can ask for a set of this sort, what elements can you throw away so that it still is a basis? Or what finite sets can you throw away such it still is a basis? And what finite sets can you throw away so maybe it's no longer, actually, this is just a restatement. This should be, what finite sets can you throw away such that this becomes a minimal asymptotic basis, or what finite subsets can you throw away? That is, it's just very hard to understand these sets, even though there's a very simple description of them. If you take any geodetic sequence, what are the partitions of n that give you a minimal asymptotic basis? So the theorem that I stated says that if each of the sets Wi contains infinitely many infinitely many sets of consecutive integers, intervals of integers of a fixed length, then you get a minimal asymptotic basis. But most partitions don't satisfy that property. Basically this problem is asking for what partitions of the integers does this construction give you a minimal asymptotic basis? And for what partitions of the integers does it not give you a minimal asymptotic basis? That's the question. And there's one particular case of these geodetic sequences I find very interesting. So remember this, in this geodetic sequence, it's a sequence of integers, and each integer divides the next integer. And if you look at the quotients, you would get some number at least 2. If the numbers are always the same, then you just have essentially the power, your geodetic sequence is the powers of a fixed number. But suppose these successive quotients, it's not constant, but they're always either 2 or 3. So you take a random sequence of 0s and 1s, or if you take a random sequence, and so you choose these successive divisors at random to be 2 or 3. You get something really very interesting. And I don't know that anyone has looked into any of the properties of such a sequence. Even if you take a very simple case, suppose we take this geodetic sequence. So GI is some number DI times G sub I minus 1. And suppose when you take this sequence of successive divisors, if you take here, this epsilon I is 0 or 1, determines whether you have 2 or 3. Suppose if you take like epsilon 1, epsilon 2, or epsilon 13, epsilon 14, you have exactly a 0 and a 1. So that means that you have a number, and if the next number is 2 times that, the one after that is 3 times that. So the g sub 2i, you know, is 6 to the I. And how do you get from 6 to the I to 6 to the I plus 1? Well, you multiply either by 2 and then 3, or by 3 and then 2. And that's a really interesting sequence. And there are a lot of questions you can ask about this, either in the context of these minimal bases or in other contexts. And it's just curious. I don't know anyone who's looked into this, but I just don't know. It may be that there's already an infinite literature on this subject, but I haven't come across it. In the last few years, there's been a fair amount of work done on the construction of minimal asymptotic bases. A large part of it by mathematicians in China, many of whom are named Chen. Yeah. Anyway, that's what I wanted to say. I mean, the problem I would really be happy for people to think about is this. You take a geodetic sequence, what partitions of the integers lead to a minimal asymptotic basis and which don't. And even in the simplest case, where we're just looking at binary representations, the GIs are just the powers of 2, this is completely unknown. Okay, thank you. Done. Let's see. Stop share. Excellent.